The dyno test of the cheaper, easier to assemble electric supercharger was supposed to be really simple. Put it on the car, put the car on the dyno, see how much power it makes. But it got real deep, real fast. Let's look at the data. If you're watching this, you're my people. And that's because you don't just want to know how much power the electric supercharger made, you want to know why it made what it made. But there's a few points I wanted to touch on before we get into the data. First of all, this was run on regular 93 octane pump gas. There was no E85, none of that. Now, I did add some Lucas octane boost just as a safety measure. I've used it before. I used to use it with the Whipple when it was running 15 pounds. It does work really well and it keeps your engine safe. The only downside with it is it does turn your plugs orange with the additive package that's in it, but it does work extremely well. In fact, I'm not sponsored by them or anything, but I'll just put a link down in the description below. There was also no tuning done to the EFI system at all. This was just a preliminary get to know you, let's see how much power it makes, because we've never tested this thing before. And finally, there was no charge cooling of any sort. The MES system wasn't activated. In fact, it wasn't even hooked up. There was no air to water intercooling, no air to air intercooling. These were relatively low pressures. And again, this was just a let's see how much power it makes. Now let's take a look at our baseline naturally aspirated pull. I made mention several times about the whole power glide issue, and that's because it really does come into play. Before we swapped converters with the exact same engine setup, the thing pulled 388 rear wheel horsepower on raised dyno. After the converter swap, but with no other changes, we lost 40 horsepower. But we did go faster in the quarter mile. So that's part of the voodoo that a converter does, and I feel that that's worth mentioning here. Now, we did pull 344 rear wheel horsepower on raised dyno, and on this day, it was a much hotter day, the weather was worse, and we pulled 339.65, as you can see on the dyno graph here. Now, peak horsepower came in at 5,500 RPM. That's right about here. It does this little weird dip, and then it kind of comes back up, and that's something that we see throughout the pulls, and I have no concrete explanation for that, because with the other converter, it was peaking at 6,000 RPM. So again, that's just some of the voodoo that the converter does, but it is worth mentioning and keeping in mind. Now, we do have a method where we can figure out the flywheel horsepower. There's actually a couple of ways that we can sort of estimate the flywheel horsepower with losses and all, but the one that I like to use because it tends to be the most accurate is brake-specific fuel consumption. So let's take a look at the Megasquirt data log, and this is what our naturally aspirated pull looked like. The white line in this top graph is RPM. The red line is actually, well, it's listed as boost PSI, but it's manifold pressure. Let me switch that over for purposes of the naturally aspirated pulls to MAP, which gives us the same thing, but in kilopascals. So 100 kPa would be atmospheric pressure. So you can see our max is 100.3. That's, you know, this is sea level. The sea is a mile away from here. So we are pretty much at sea level, so that makes sense. In fact, where this cyan line is right now, that's pretty much where we started. It's 99.2 there, but it kind of goes up and down, like there it hits 100. So we started at that point. Now there is a slight restriction in that intake manifold, even with the gigantic 100mm throttle body. I don't know if it's in the throttle body or if it's right behind the throttle body due to the shape of the intake manifold, but there is a little tiny bit of a restriction that we can see when we go all the way up to 6,000-ish RPM. Here at 6,100 RPM, we're down to 99.1. Not huge. I think our lowest number is here, 98.6. But, you know, it's not huge, but it's there. It's also worth mentioning. Now, let's look at the brake-specific fuel consumption at peak power that was observed at the tires, because that's what matters. That's what you're putting to the ground. So again, it was 5,500 RPM. So let's go to 5,500 RPM on the data log here. And it does vary a bit. So it's somewhere in here. Let's call it here. So our duty cycle in this lower graph, the duty cycle is the white line, is showing 39.1%. Now that's a percentage of the maximum duty cycle, which would be 100%. This car has 8 80-pound injectors. So 8 times 80 is 640. So it can flow 640 pounds per hour of fuel. That's a lot. But keep in mind, it was designed for forced induction. It's basically my forced induction rolling test bed, which is why it's only seeing 39%. But we could take that 39% number and that 640 pound per hour maximum fuel flow and figure out what the horsepower number is. So let's bust open with the computer's handy dandy calculator here. So you take 640, that's the maximum injector flow, multiply it by 39%, which would be 0.391 in this case, if we want to be accurate. And that gives us 250 pounds per hour of fuel flow. Now, brake-specific fuel consumption of a well-tuned naturally aspirated engine, which the LTD is a well-tuned naturally aspirated engine. You know, it's got really good aluminum cylinder heads. They're trick flow twisted wedges that have been ported and made 3 trips to a flow bench. The intake manifold has been chopped within an inch of its life. In fact, I cut over 11 pounds of aluminum out of it. It's got a decent camshaft in it. It's a healthy 365 cubic inch, 8.2 inch deck, small block Ford. So that would probably have a brake-specific fuel consumption in the 0.45 range, I would assume. But let's go with 0.5. That's actually going to make the projected horsepower lower, but it's a safer bet. It's a more conservative bet. So we take 250.24 pounds per hour of flow divided by 0.5, and that gives us 500.48 horsepower. Now, I happen to know that the engine in the LTD does make 500 horsepower naturally aspirated. That math works perfectly. And perhaps you're thinking, that's a lot of loss to go from 500 horsepower to 339. What is that? That's like 161 horsepower. Well, there's a way, if we look at the dyno data, that we can see exactly what at least the slip, and I hesitate to use the word slip in the converter because that's not really what it's doing. It's converting. It's doing its magic. There's a stator in there that redirects the fluid inside the converter, which adds additional rotational force to the input of the transmission. That's how it multiplies torque. It's a lot easier to see how that works in an animation, but it took me years to figure this out, how a converter actually works, but that's not the point of this video. But we can see what kind of mile an hour it should have been running at the RPM where it made peak power. So the way we can figure out the amount of converter slip using the dyno software is actually kind of cool and it's pretty handy. So we'll keep the engine RPM down on the x-axis, and we know we made peak power at, once again, 5,500 RPM, so pretty much right here. And on the right-hand side, we can switch it over to mile an hour. So we go to general and speed, and boom, there's your mile an hour. So at 339 rear wheel horsepower, the wheels were spinning at 121.61 miles an hour. How do we figure out how much torque converter slip there was there? Again, slip is not exactly the right word. Well, let's go to an RPM calculator. Now, I like to use Spicer's RPM calculator. It's accurate, it's handy, and it works really well. So the rear gear ratio is 3.08. The tire height is 25.7 inches. The engine RPM that we're interested in is 5,500. And the transmission gear ratio, it's high gear, it's 1:1. So let's see how fast it should have been going. 136.59 miles an hour. And again, how fast was it going? 121.61. So let's call that 135 versus 121. So there is some slip going on in the converter. In fact, it's 14 miles an hour. Give or take, but close enough. So we take 14 miles an hour and divide it by 121.61, and that gives us a slip of 11.5% just in the converter. So we're losing 11.5% power just in the converter, naturally aspirated. Keep that number in mind because when we start adding boost, the numbers get way bigger. So if you subscribe to the notion of percentage loss, typically in a manual transmission car, you'd see about 15% to 17%. So 15% plus approximately 12% gives us a 27% loss factor. So if we take 500 horsepower and multiply it by our 27% loss, which would be 73% power making it to the rear wheels, that gives us 365 horsepower. That number is a little bit higher, obviously, than 339. It's 26 horsepower higher, but we have a situation where the weather's 95 degrees, the straps are pretty tight. If you watch the dyno cheat codes video, you'll know what a huge effect strap tightness can have. There's a bunch of other variables, so it's pretty close. It gets us in the ballpark. So now let's take a look at the first electric supercharger pulls. Now I did go through this data in detail already, and I did find out one interesting thing that I assumed was the case that turned out not to be the case. You know what they say when you assume? Yeah, that kind of happened here. So what my assumption was that the Vortec SI trim compressor map is exactly applicable to the Speedmaster P2 compressor map. That turns out not to be the case. It's a little bit off, but it's off enough where I can't sort of fudge the numbers to make them work, at least not reliably so, and hold my head up high and say that I'm telling you all the truth. And the relationship does not appear to be linear either. So I'm going to do another video where I actually take one of the P2 blowers apart and compare it with the impellers and stuff that I have from the Vortec superchargers. But we're not going to use the compressor map here because, again, the data doesn't exactly correlate, and we'll find out specifically why again in that future video. But let's take a look at the dyno graph here. So we made 407.83 rear wheel horsepower with the 14-tooth motor and 18-tooth impeller pulley combination on the electric supercharger. That's a pretty good gain. That's a gain of 68 rear wheel horsepower. Peak power is about the same, happened roughly at 5,500 RPM. So first, let's take a look at the Megasquirt data log and do the brake-specific fuel consumption calculation to figure out what the flywheel horsepower was there. And then we're going to see how much converter slip. Again, not really slip. The converter is doing what converters do, which is torque convert, but it's going to show up as slip on the dyno and see what that number is. So let's pull up the Megasquirt data log, and here it is. And let's look at about 5,500 RPM, which is where we want to see what our duty cycle was. Our boost pressure, by the way, we're still in map, so let's switch that back to boost. There's boost. 2.3 PSI. So at peak power, we made 2.3 PSI of boost with the first pulley combination. And our duty cycle right here was 44.5. It does vary up and down, but that's actually kind of in the middle of it, so that's a good one to run with. 44.5. So let's go to our handy dandy calculator and take our total fuel flow, which again was 640 pounds per hour, multiply it by our duty cycle percentage, which was 0.445. That gives us a fuel flow of 284.8 pounds per hour. Divide that times a BSFC of 0.5, and that gives us 569.6 flywheel horsepower. Now, we saw a gain of 68 horsepower at the wheels, but we're only picking up 69.5 horsepower at the flywheel according to the BSFC calculation. Well, why would that be? Let's take a look at the converter slip numbers. So again, on the right-hand side here, we're gonna, instead of none, we are going to replace this with speed, mile an hour. And at 5,500 RPM, we were going, it's the blue line, we were going 112 miles an hour. Now, let me move this out of the way. You see how the blue line kind of starts to pull back, and you get the same weirdness happening here where it comes back and it's registering 142.88 miles an hour. That's not real data. That is because I did not stop the data acquisition before I let off. I let off first and then stopped the data acquisition on the dyno, and that's what you get. So that's, that's on me. I was nervous. What can I say? But we were going 112.6 miles an hour as opposed to 121 before. So that's a pretty big difference. So let's go back to Spicer's speed and gears calculator. All this stuff stays the same. And nothing really should have changed, actually. We should be going 136.59, but let's call it 136. And back to the dyno graph. And we were going 112.6, so let's go 136 minus 112. That is 136 minus 112. It's actually pretty easy to do in your head, but I'm choosing not to. It's 24 miles an hour. We take 24 and divide it by the speed we were going, which is 112.6. And that gives us 21.3% slip. That's a lot. Let's look at it from a pressure ratio perspective. So we know for a fact that we made 2.3 pounds of boost, right? So if we take 2.3 PSI and divide it by 14.7, that's 0.156. You add a 1 in front of it for atmospheric. That gives us a pressure ratio of 1.156, which gives us a number to work off of. So if we multiply that times our naturally aspirated number, which is 339 rear wheel horsepower, we get 392. That number is still a little shy of what we actually saw. We saw, again, 408 horsepower at the wheels. What's going on here? It could be any number of things. It could be that even though the converter slippage is accurate, that number is definitively accurate. It may not be taking into account the fact that we're shoving more power through the converter, and therefore the converter might be actually multiplying torque at a much higher RPM, giving us more power at the wheels than the losses would normally dictate. In fact, I would say that's probably likely what's going on here. There's other factors at play, like for example, when you compress the intake charge, the flame front travels faster, which means you need less spark advance, and we do have less spark advance happening here. We can look at that on the Megasquirt data log here. Our spark advance is the green line on the bottom graph, and at peak power, we were seeing 25 degrees of spark advance. We were probably seeing about 27 naturally aspirated at the same power level, but given the density of the charge is greater, maybe it was seeing effectively a faster flame front and effectively more timing. That could be a thing that's going on here. But I really think that the biggest factor at play is the torque converter is multiplying torque at a higher RPM because it's just simply seeing more power. But there is one last piece of the puzzle that we haven't looked at for the first electric supercharger pull, and that is the ESC data logs. This is a screenshot from my cell phone because there is no way to data log to a computer, so I had to take a screenshot, and here we are. But anyway, we're seeing 286.5 amps at 44.4 volts. We were seeing an electrical RPM of 63,290, and electrical RPM translates to mechanical RPM through pole pairs in the motor. And what that means is a Castle motor has 4 poles. That means it has 2 pole pairs. So you would take 63,290 RPM and divide it by 2, and that will give you mechanical RPM. So let's just go ahead and do that. Let's see, it was 63,290, and we divide that by 2. The motor was spinning at 31,645 RPM. Now, with the 18-tooth impeller shaft pulley and the 14-tooth motor pulley, there's effectively a pulley reduction happening. 14 teeth on the motor divided by 18 teeth on the impeller gives us a ratio of 0.77 repeating. So we would take that 0.777 repeating, multiply that times our motor speed of 31,645 RPM, and that gives us an impeller speed of 24,588 RPM. And again, at that impeller speed, we can't really look at the compressor map because of what I said earlier. There is no direct translation, at least no solid enough correlation that I can find yet. We're going to work on that. We're seeing that we are pulling 44.4 volts. That's the voltage sag because the pack starting voltage is 50.4 volts and a current of 286.5 amps. By the way, the power draw for that is 44.4 times 286.5. That's 12,720 watts divided by 746 watts per horsepower. That's 17 horsepower out of the Castle motor. That's pretty close to its limit. That's about where it should be happy running, which is why I'm glad that the bigger Castle motor and ESC are on their way. So that is the first pulley combination. Now let's take a look what happened when we really jacked things up and went to the 22-tooth motor pulley. So here is the dyno graph of the 22-tooth motor pulley dyno pull. Now I'm going to use the first pull because after the electric supercharger kicked out, I wasn't sure what happened, but instead of doing the smart thing and checking the data logs, I just assumed it was the AFR safety system and it was running lean, so I richened it up. And it turns out it was not running lean. In fact, it was a little bit rich, and I just made it richer, which is why we lost a little bit of power. But the first pull is the pull that we're going to look at as a result. So here it is. It's the green trace, and our max power was 453.67 horsepower at 5,320 RPM. Now that's really interesting. So we did not see a huge drop off in RPM between the naturally aspirated pull and the much lower boost electric supercharger pull, but we're starting to get fairly significant. We are seeing a 200 RPM drop now for the peak. And that, again, is because it's making a lot more power. So let's take a look at the Megasquirt data log of that pull. And here you can see the red line is boost. You know, it ramped up pretty quick, but then it only ran for, what, about 2 seconds before the electric supercharger, specifically the ESC on the electric supercharger said no more. That was a second and a half before its safety kicked in. We did see a peak boost of 5.4 psi, which is starting to become significant in the boost world. And at peak power, which was again just over 5,300 RPM, let's call it here, we're still at 4.9 psi of boost, which is pretty good. And our brake-specific fuel consumption, it actually went down here a little bit, but whatever, fair is fair. So it's 50.4. So let's do our typical calculation and see where that lands us. See if it's any closer than the lower boost pull was. So again, we take 640 pounds per hour of flow, multiply it times 0.504. That gives us a fuel flow of 322.56 per hour. Divide that by 0.5, and that gives us a flywheel horsepower figure of 645.12, which I think is actually pretty close. Future Alex here, coming at you from the editing suite because somehow I managed to forget to do the pressure ratio calculation. Let's see what the math says we should have pulled rear wheel horsepower wise using the 4.9 psi of boost pressure that we saw. So we take that 4.9 psi, we divide it by atmospheric pressure of 14.7. That gives us 0.333 repeating. Then we add 1 because of the atmospheric pressure that already exists, and that gives us a pressure ratio of 1.33 repeating. We take that number and we multiply it by our actual horsepower figure, which naturally aspirated was specifically, and I'm going to use the whole figure for a reason, was specifically 339.72 rear wheel horsepower. Let's see what that works out to be. So we take this number, 1.333 repeating, which again is our pressure ratio, we multiply it times 339.72, and that gives us 452.96. Basically 453 horsepower is what the math says we should have pulled. And what did we actually pull? 453.67. How do you like them apples? It's actually a little bit better than that because, you know, this happened 200 RPM lower, but I can't believe I forgot this. The math works beautifully on the higher boost pull. So before we wrap up, let's take a look at the ESC data log because this is where like the mind blown moment occurred for me. It pulled 664 amps peak. Actually a little bit more than that peak, but that's close enough to peak. And the voltage sagged down to 41.1 volts. So, you know, that's 664 times 41.1. That's 27,000 watts. That's 27 kilowatts. Now that's peak. Let's say it leveled out around 600-ish. Let's be reasonable, and let's say the voltage sag isn't quite that much, so let's call 600 times 42. It's 25,200. Divide that by 746 watts per horsepower. That motor was pumping out almost 34 horsepower. Peak, more than that. Way too much for that little motor. But this also indicates that the electric supercharger was going like way into choke, because that's why the power jumped up by more than double. And the impeller wasn't spinning that much faster. So if we look at the electrical RPM was 50,420, divide that by 2. That gives us 25,210 motor RPM. And the pulley ratio of 22 to 18 teeth, I actually know this off the top of my head, it's 1.22, repeating. So we're going to multiply that by 1.22. We hit over 30,000 impeller RPM, close to 31,000 impeller RPM. Now it's worth noting that the sledgehammer actually pushes to like 32,000 to 33,000 impeller RPM going down track. So this is pretty darn close to that. But it does appear to be going pretty far into choke. And this is only a little over 5,000, like maybe 6,000-ish impeller RPM more than the 14 and 18 tooth setup did. That's some food for thought there. We're gonna have to see what the bigger Castle motor and ESC do. It's got a lower KV, which is RPM per volt rating, so it should run in a much happier RPM band. It's gonna be a little bit lower than this, but it should make good, repeatable, and durable power. So, you know, definitely stay tuned for that. This has been kind of a bit of a weird one. This is the first deep data dive where the numbers didn't line up like within a couple of horsepower. Things are kind of all over the map, and the only thing I can think of is that the torque converter in the Power Glide is playing havoc with our numbers. We are going to compare the difference between the actual mechanical differences between the compressor side of the P2 supercharger versus the Vortec SI supercharger, because this one does appear to be going into choke a little bit earlier. It also does appear to make a little less boost. Now, those are negatives, but the boost does appear to hold on much better than the Sledgehammer does. So that's positive. And that's actually overall, that's more of a positive, because what's happening there is you're putting in less cylinder pressure at peak torque, and peak torque and high cylinder pressure do not go well hand in hand together. I have boxes of pistons that prove that. So thanks for coming along on this sort of weird deep data dive. And of course, I didn't forget your moment of Roger.